Just to start out, there's kind of a lot of people, and we're closely aligned with Randy Bartle's group at Colorado State University. And as you'll see, we're recently teamed up also with Jeff Broderick, Epilogue Laser. If you've ever purchased a laser engraver, they're also in Golden, Colorado, and they make their own CO2 lasers and everything. But they're actually helping us make some of the masks that I'll talk about as we go along. So. And my computer's not letting me advance. Okay, there it goes. Okay, just a long. Yeah, so I thought, gosh, since it's neuroscience, so if you're into pedagogy at all, you know that almost anything I do other than stand up and talk in front of you like I'm going to do for the next hour would help you retain information better. So, so this is one of the poorest ways we can help you retain. So I always like to add art to stimulate the other side of your brain as we're going along. So you get the whole brain stimulus. And as the theme of the art gets darker and darker, you'll know we're getting closer and closer to the finish of this. So that's the method to that madness. So I threw in some stuff first on just how do you characterize a pulse at the focal plane of the microscope. And so we've done quite a bit of that, and we can kind of, based on what your feedback is, I can go a little bit faster through that or as needed, but just to give you a sense of different methods that you can use. And really it comes down to a new one that we developed that has, I think, some really nice intrinsic benefits for this community. So I do want to kind of put a disclaimer. So I thought as a workshop, this isn't an overview of all the methods. It's really the ones that we've been involved with because I can comment on them directly. So if you have questions as we go along and how easy is it actually to build in the microscope or whatever, I can do it. And then as we go through kind of like the spatial frequency modulation imaging in particular, where we can produce enhanced resolution, it's big on concept, very short on the mathematics. And so just to hopefully plant that intuitive and conceptual understanding. And if there's any follow-up you want, we've worked out it in quite detail in all these areas, so I promise to follow up on that. So yeah, why do you want to characterize pulses? So I kind of find this intriguing. So for quite a while, like with Carsten Koenig's paper ages ago, so 1999, they really showed that the shorter the pulse, that can really lead to damage in biological systems. And so for me, it's always been a quest then to help quantify really rigorously what is the intensity that you have at focus, so you could really communicate those conditions between microscopes and microscope designs. But here we are almost 20 years later, and this is from one of Chris Yu's paper, and they make the comment that there's still this huge discrepancies in photo damage. And there's still, when I look through a bunch of papers in multi-photon imaging, it's rarely reported, if ever, actually what is the intensity at focus, where, I mean, they've really included a measurement of the pulse duration, et cetera. So I'm kind of still on my quest to help do this, and I'm going to give you now a smorgasbord of ways to do this. And again, I apologize, it's parochial, it's really from my perspective. And then I'm not sure what the background of everyone is, but this is the way we like to think about it, is that, if you assume a pulse shape, here we're just assuming a Gaussian, and then we take the Fourier transform of that. Now we've got the Gaussian field spectrally. And then to propagate it, we just multiply the field in terms of E of omega there by the spectral phase, phi of omega. And that phi of omega is something that we can actually calculate for the optical systems. Like Spencer's done a fantastic job at showing, like, you can use tools like Zmax to calculate all the optical path lengths as you're going through the system and really figure out in a real nice, rigorous, quantitative way all the different delays that are involved with that, the dispersion of the system as a function of wavelength. And then to develop strategies in terms of compensating for the dispersion of the glass of the microscope, the lasers, and it can be very spatially varying. You want that phase to be as flat as possible, but the tool to help develop strategies to mitigate any deviations of the phase, it's nice to do a Taylor series expansion on the phase and understand what each one of those terms does. And if you understand that, for me, it's always been very helpful to, then I can say, okay, I need to knock out these different orders. And it's really just like you would spatially. So for example, if you've got spherical aberration in your system, a super simple way to combat spherical aberration is to add defocus. And I teach modern optical engineering, and so I always like to joke with my students, you have to add defocus and not defocus. There's two types of defocus. I can go into that later, but if you add the correct defocus, you can add a second order aberration that starts to combat this fourth order aberration of spherical aberration, end up with a better image. Okay, and we can do the same thing in time. Everything holds. We can add. You can end up with a fourth order spectrally, broadens your pulse, but we can add second order to start to combat that. So very, very similar. So again, you want to make this as flat as possible, but part of the strategy is to do this Taylor series, understand what each term is, to kind of develop different strategies for combating this. So I'm just going to, that's my favorite form for expressing everything just in terms of the path length, especially through the different glasses. And then when I look at the different Taylor series, they're named at this point. So we've got just the first order group delay dispersion, third order dispersion, and fourth order dispersion. And we can show you different data where, especially like for bleaching characteristics and stuff, you can really, there's the good argument to say you want to correct all the way through fourth order, actually. So those are our terms. What do each one of them mean? So that's what this slide shows. Do I actually have a laser here? Yeah, so it's weird though. Yeah, it's weird. But anyway, so there's my pulse spectrum. And if I Fourier transform that gets me to B. So there's, oh, thank you. Yeah. So I'll try not to actually shoot anyone. Okay. Oh, no, yeah. No, this was nice. Okay, so there's my spectrum, Gaussian, there's my pulse. And so the first term in our Taylor series is group delay, so that just shifts our pulse in time. Okay, so that's usually one we're not worried about. Except it turns out that when you start going through your complex optics, you can end up with a radially varying group delay. So the light that goes through the marginal rays and the light that's traveling down that chief ray may actually arrive at different times. So your integrated pulse width at the focus could actually be much larger than what you think it is. Group delay dispersion, now that's where the different wavelengths start to walk off from one another. And so they actually start to stretch your pulse. So now it's going down, it's getting longer. And if you're using all these nonlinear processes to generate image contrast, the efficiency at which you're doing that is starting to diminish. Okay. Third order dispersion, so we're turning on each term individually and turning off all the other ones so you can really isolate and see what each one does. Third order produces a pulse asymmetry. And depending on the side of the sign of the third order, you can get these pulses to go in the leading or trailing edge. Okay? And then fourth order starts to broaden the pulse as well. So that's what everything's doing. And then, but in general, you can see a trend. So even orders are going to tend to broaden your pulse width. Odd orders are going to throw asymmetry into the pulse shape. All right? So we really want to then come up with a way that, yeah, can I design a system so I've got something of equal sign and opposite, or of equal magnitude but opposite in sign. So by the time I'm at the focal plane, I'm really looking like this, getting the most efficient excitation. And I think Spencer talked a little bit about this yesterday. So here's a super simple table that says, okay, for working in the kind of the normal dispersion regime, what signs do I end up with? So most of your glasses, you're going to end up with positive group delay dispersion, positive third order dispersion. And so now if you want to mitigate that, you might say, okay, I'm going to use gratings. So in a standard grating configuration, those are going to have negative second order. But here's the challenge. It's got positive third order. So I'm going to be able to set my gratings to knock out this term, but the third order is going to be residual. It's going to add to the glass that you already have in the system. So prisms, oh, that's looking better. So it's got my negative second order, and it's got negative third order, which is great. So that means it can actually start to attack the third order of the glass inside your microscope. But the important point here to realize is that especially as you start to push the pulse width down, the rate that you are compensating for the third order dispersion, and I can give you these numbers, with prisms is different than the rate that you are accumulating third order dispersion from the glass. So what happens a lot of the time is that by the time you've added the group delay dispersion that you need to compensate for the second order dispersion of the glass, you actually end up overcompensating. So you actually end up, because these are not matched, the plus and the minus, they're different in size, but they're not matched at the magnitude that you need. So you actually end up not being able to get back to a short pulse because now your pulse actually ends up with residual negative third order on top of it. So one of the things we did a couple of years ago, quite a few years ago now, is we developed Grisons. And as you can imagine, Grisons are the best of all possible worlds. It's gratings written onto prisms. And so what's cool about Grisons is it's got the right second order, and we can dial the dispersion of the Grism at your wavelength such that the rate that it is knocking out the third order is exactly equal and opposite to the rate that you're accumulating with glass. So you can end up with quartic phase compensated systems with Grisms. Yeah.
Before you move to the next slide, is there a standard rule about the group and the third order dispersion for instance, like Bragg layers, when you make a filter, for instance, you shoot your bulb through an excitation filter. Is there a significant dispersion that those devices add to your?
Yeah. There can be, I guess.
Can you go either way, or is there a rule where
they can go both ways, and they're usually polarization dependent.
Oh,
yeah, so I would.
Really huge GDD.
Yeah. Because the one that I don't mention here is you can do coatings these days. You can really take advantage for using coatings to compensate for these as well. So.
But in general, you would have a coating that compensates for that, but you would pay for it at the expense of transmission efficiency, maybe?
It could be super high. A lot of these coatings you can.
It's probably super wavelength dependent.
Okay. And it's
So just to elaborate on what you just said, so the pre-comps, the manual of single prism pre-comps that I showed you downstairs, we had originally made them with SF11, which is a pretty commonly available glass, but it's not super dispersive, so we weren't getting quite as much compensation as we wanted. Swamp Optics made us custom prisms made out of PBH71, which is this heavily leaded glass, a little bit harder to get, but it gave us much greater GDD compensation, but it also has massive third order, and that could have killed us. It turned out just in practice that it didn't. But this is something that you can model. So CMAX is the easiest way to do it because they have all these classical tubes. But there's, I don't remember the exact website off the top of my head, but if you ever wanted to kind of do a toy example to kind of see how you can work through these things, you can get full, index of refraction as a function of wavelength for a bunch of different classes, and you get the full function. You can fit that with an analytical function if you want, if that's easier to do in the analysis you want to do, or you can use it as a lookup table. But that's basically all ZMAX is doing, right? They basically just have a giant database for these different classes.
Calculate that path length P.
Yeah.
It's a function of wavelength.
It's super easy.
Yeah. So that's kind of the things to be aware of. So now how do we measure the pulses? So this is kind of going back in time. So the one easy way to do it is to really just take advantage of whatever fluorophore that you're using to label your system with. So you can literally build, so here's our pre-compensation unit. We go in and out through that. And then we come over here. So this is basically a Michelson Interferometer. So it creates two pulses that we can time delay with respect to one another and drag them one across the other. The one cautionary note, I was actually, so as I put this together, so this is 1995. You want to use a balanced Michelson Interferometer on all of these. So you got to make sure that your transmission and reflection and your transmission is the same through both arms and the coatings and everything to get a true autocorrelation and not a cross correlation. And I was happy to see as you go along through 20 years of building these devices, I at least built it consistently. so as we look through each one. So this one's neat though in the sense that now you've got two pulses that are going. You can actually have some dye here. And now you can detect that fluorescence wherever you want, wherever it's convenient for you. And you can actually just measure the autocorrelation trace, which starts to give you a sense to how well you're doing with the pulse. And so it is collinear, so you get fringing on it. And it really follows a distinct formulation where there's this envelope that gives you an 8-to-1 contrast. If you're not getting that, you got a problem. Here I think you can already pick out those. So first we did it, so this one was with a doubling crystal. And here we're doing it with a dye, and you can already see a kind of a distinct shape difference between those. These are pretty short. These are around 50 femtoseconds. So in all these I've tried to give a couple of, so the advantage of this technique, it uses dyes that you're already, you know that they work, so you can just take advantage. So you could do it autocorrelation at any point in the brain of your animal if you want to. And then you can actually shift these off of one another spatially. You can measure your beam focus spatially as well. Okay, the disadvantage in my opinion is this guy. It can be a real pain to implement, and you got to pass through the pulse width. So that if you're using 100 femtoseconds, that's 30 microns. That means you got to have these guys matched within less than 15 microns. So it's a little bit of a pain to build this guy. And then finally, there's no phase information of your pulse in this kind of a system. But you do it at the full NA. So, and then what we found really quickly is this 8-to-1 was really telling point for us if we had spatial aberrations. So if we fill the back of the objective, that 8-to-1 would in general go away. And it was really due to the radially varying group delay that might be present in the objective. So in general, we're always using just a thin ray that goes down the center of the system and then scanning it around to take a look at things. Because otherwise, this starts to deviate. So you can really use these right away to measure other aspects about how well your system's performing. So take a look at the noise from that. And as we kind of progress, this is one of my, the other ways that I really like to do it, is to just use these gallium arsenide phosphide photodiodes from Hamamatsu and just look at the signal, how much the signal to noise improves with this guy. You can really do it just simply with room lights on. And we used to be able to, I think they actually have them. So when this first started, you'd have to write Hamamatsu and go through their impossibly complex purchase ordering system and say, could you please remove the window off of this diode? And they would. And so it cost about $100 to get this photodiode. Once they remove the window, then you can really use it with a small working distance objective. And in this case, we did it 1.25 oil immersion. And it really gives things that are just beautifully clean. So it's very nice, simple way to do it. And then I always like to show you that then we could drag it through. We could actually measure the axial sectioning for this system as well. And it's super inexpensive, great signal to noise. And it really works if you're doing if your excitation beam goes from 600 to 1300 nanometers, you can use the same $100 detector.
So,
yeah.
Just so I'm understanding this correctly, you generate two-photon absorption in the photodiode and those photons?
Yeah.
How?
So you're sweeping out that photocurrent.
How
that two-photon photocurrent.
Is it just because the photodiode band gap is high enough
Yep.
that you don't pick up any of the IR?
Yep, that's right.
How do you know you're not picking any IR?
Well, yeah, so what you do is you actually shortchange this through here.
Have you seen the spectral response for gas? It just
it drops.
Yeah.
And then what you really do is, again, this is how we find it in the lab, is you actually cut down, you really make sure that your signal's purely scaling as 2 photon.
Okay. Yeah.
So we do that consistently. Yeah,
Wow.
so we just always make sure. But again, this one you can do with the room lights on, really easy, non-toxic. The biggest danger in this one is these leads, if you don't make it break off from time to time. So that's about it. So things are looking cleaner and better. And then the other way that I like to do these, just the autocorrelations, is now you can do it with a cover slip, but use third harmonic. So, and again, so I don't know if you keep notes. Look, so as the years pass, my interferometer is still staying the same, still getting it balanced everywhere. But this one, once you go to the third harmonic, you got to recalculate things, and now the contrast is 32:1. But that's okay. So this is literally measuring, this is this is a short pulse, 19 femtoseconds. And this is at 800 nanometers. So we really just have the cover slip. You focus on the back side of that cover slip. And when you go to the back side, you have a huge index change between the cover slip and the air. That means you're going to get copious amounts of third harmonic with that large delta N. And you can literally just push your PMT right up there. So even though I'm at 265, this for the third harmonic was no problem to detect. And so I really like this one too in the fact that it's just, we've done it from 800 nanometer excitation wavelengths from 800 nanometers to 1.5 microns. So just, again, real easy to do. And also at that point, the other nice thing about this is that you can see how clean it is, and it's just, again, the wavelength separation between your excitation wavelength and where you're detecting is so big, it gives you super clean stuff. Okay, but all of these are still got these, balanced scanning interferometer, but again, no phase information. So essentially, I'm always assuming things, which is annoying. So what we really wanted to do, Mario. Yep.
What's the KDP crystal? What is that?
Oh, yeah. So we always kind of want to benchmark, when we develop a new pulse characterization technique, we want to benchmark it against a known method to see how it compares. So what we did over here is, this was a kinematic mount. So you could pull this out, you could go through an off-axis parabola, and you could just generate second harmonic using a nonlinear doubling crystal. And we could do a second order, SHG interferometric holographic to really compare how we're doing.
Oh, okay.
So that was just our control. Okay, so we'd like to do better. And so we want to get that phase information. And we want to stay collinear so you can really use it like you would inside the microscope, and go even to the full NA if you would like to. So we'd like to do something like, based on frequency resolved optical gating, techniques developed by Rick Tribino. And what we did at first is we really could put a doubling crystal here, and we could do second harmonic interferometric images, and then we spectrally resolved that. So we ended up with spectrally resolved autocorrelations interferometrically that in principle have the phase encoded, and in practice they're great artwork because they're just so complex and data intensive that they weren't really practical. So we really collaborated with Rick Tribino, and he had he came up with a simple solution for us. So here what we did is that, okay, now I've got there's my autocorrelator rearing its head again. But rather than using type 1 phase matching, you use what's called type 2 phase matching. So what happens is that now you put wave plates so that the polarization in each of your arms is orthogonal. And that means these beams can no longer interfere to give you fringes. So now we completely have gotten rid of all the fringes that you've seen on every slide before. And now I get a second harmonic signal, and so I'm using this, what we call type 2 phase matching, which requires these guys. And the gating's being done at this crystal. But now I can just collect that second harmonic light, and I can spectrally resolve it, and I kind of get this classic frog trace where we've got the delay versus wavelength. And that's all the information I need at that point to be able to really extract out the amplitude of the pulse and actually directly measure its phase at focus. So this is nice. So this is big. So fringe-free, collinear, yeah. No pulse shape assumptions anymore with this kind of a system. I can really extract out exactly the phase in a quantitative way. The disadvantages, okay, I still got this scanning interferometer that's a pain to set up. And now I got to have a type 2 doubling crystal, which is not too bad actually, but yeah.
Can you elaborate on how you go from the top right image, that frog image, to the trace?
Yeah, I was realizing that as I was talking about that. Yeah, I mean, yeah, maybe we'll have to have a little bit during the break. Maybe I could draw something on the board to show how to interpret those. But basically what you're doing is you're really gating. You're really saying, okay, I really want to start to take a look at how the wavelengths are arriving relative to one another. And if I can get that information out, that is the spectral phase. But yeah, so it's not obvious, but that's yeah, it's these traces that enable us to do that. So, but there's good news on the horizon now. So it turns out that after I got inspired by this, I realized that, wait a second, I can actually pull a really clever trick with my cover slip in third harmonic. And so that gave us third harmonic generation frog inside of a microscope. So now I've got the same interferometer, and if you've done any kind of third harmonic imaging, so the third harmonic goes away with perfectly circularly polarized light. And so what we do is now if you stick a quarter wave plate here, you've got left and right circularly polarized light basically, but you can get rid of the fringes for this third harmonic frog as well. So now I can do fringe-free frog traces using my cover slip again. So now I'm back to not having to use the type 2 phase match system, but I can just literally stick a cover slip here and I can collect the light that's going here into my spectrometer. So I get the requisite wavelength versus duration, and I can extract out the amplitude and the phase of my pulse. And this is the way you want to look at things. This is one of the things that I mean, I want to kind of make a point. So working with Rick, I mean, for me, it's really the gold standard. And I always I've learned a lot from him. And so this is what you really want to be able to do. When you use these systems, you want to look at, here's your measured data. When I retrieve this through this process, I'll try to get up at the break. Do they overlap with one another? How well? That tells you how good your measurement is, basically. If the measured and the retrieved system don't overlap, you haven't made a good measurement. And this is kind of one of the big misconceptions in pulse characterization. A lot of people say, oh, I didn't get a good retrieval. They don't overlap, so frog doesn't work. And no, it's letting you know you made a bad measurement. It absolutely, positively works. And then you can actually compare the differences between these two in a quantitative way and really get a rigorous bounds on your measurement. And I think for a while, I'm pretty sure that we'd always submit, there was a little bit of a game in the community about who had the lowest frog error. And I think this had the world record low frog error for a while. So it was a really rigorous. But anyway, so we're getting there. So lots of nice advantages. We've got a cover slip, background free, and it works with a broad range of wavelengths. Now we can get the amplitude and phase of our pulse out for the first time. It's still got this annoying scanning system, though, which can be difficult to implement on the bigger systems. So, but now I want to just kind of show ways that we use this. So this was one of our very first systems where we're able to image with multiple foci simultaneously. So we've got here we just split up the beam. We got one long arm. We're delaying them with respect to one another. So we switch to photon counting, and we can do multiple depth imaging, et cetera, et cetera. But what we realized is as soon as we've gone to a multiple beam system, now you've got your interferometer that you need built into your system. So if you're using one of these, what we did is say, okay, well, this arm was made longer than this arm. so to push them out by nanoseconds so we could do photon counting. But what if we just added a flip mirror here, and we've got on a little stage that it could provide a delay? Oh, I can actually scan these two arms relative to one another and make a measurement. But in general here, in this case, we had basically a deformable mirror in this arm and nothing over here. So that means the glass in the two arms is entirely different. It's not balanced, but it turns out that's okay. You can do what we call blind frog. So we could actually, we stuck our mirror here and we took those traces that you saw and we can recover both the amplitude and the phase of each arm simultaneously. And so there's, oh, and then, yeah, so it just shows how useful it is. So there's our, from the two arms, that's where you kind of start out, but, and then ultimately this is where we ended up when you start using this. So there is this, when you've got a system like this, just kind of a reminder, you can actually, you've got things built in, so you could actually take advantage of that symmetry as well. Okay, so yeah. And again, but this one requires a type 2 crystalline. We could go back and also do this with the third harmonic as well. So we've moved on. This is a method where if you've ever done this of just pure linear, and so, and again, this is, I got so many of these that they might not be, if you're interested in them, I can kind of draw some of these schematics on the board as well. So this is doing what we call spectral interferometry. This is a pure linear method where we actually have built an interferometer. We've got two pulses time delayed with respect to one another. And in one arm of that Michelson interferometer, we've placed in an objective. Okay, so that's imbalancing that interferometer. But then what we take is we take the output of that Michelson interferometer and we spatially resolve it on a spectrometer.
Don't you get the footprint of the objective's dispersion in there?
Yes, that's what we want. Yeah, that's exactly what we want.
Oh,
so
okay.
yeah.
The purpose is to characterize not the pulse but the objective.
Yeah, exactly.
Yeah.
That's exactly right. Yeah, because yep, and that's what we've done. So, and this one just shows, so we generate these spectral interferograms where you've got wavelength on this axis and the spatial dimension over here. So you're assuming radial symmetry. If you want to really, if you got an anamorphic system, you got to kind of rotate it or whatever to look at it. But this is just kind of a nice series where, let's see, I can look at some of these. Oh yeah, so this one's, I think this is like I think this is the Newport A sphere. So it doesn't have spherical, but it's got chromatic aberration. And so you can actually see these fringes change along this wavelength axis. So this is spatial. This has got, hopefully you can pick it out, it's got a fourth order phase on it. So this one's really corrected chromatically, but it's got spherical aberration on it. And then down, this one's both, where we've got spherical aberration and chromatic aberration. So at the end of the day, this is just a really neat way to kind of fully map out the performance of your optics separately in a linear fashion, if you're interested. So, so it's very, very easy. You've got to build an interferometer for it. And now, so then, but as long as you're doing that, so another neat way, so here, and it's tough to see, but these fringes right there are a result of the fact that we've got two pulses that are time delayed going into the interferometer. And then Rick and company, they actually did something super clever, which I love, is they said, okay, I'm going to take two pulses and I'm going to go into a spectrometer again, spectrally resolve them. And again, just to kind of plant all the seeds of what these techniques can do, and if you want more of the details of exactly how they work, come see me later. But what he did is now these guys are all timed up relative to one another. So he's gotten rid of the vertical spacing that is a result of the time delay of the two pulses. And he did something really clever, is he's got them coming in at slightly different angles. So now he ends up with these horizontal fringes coming through the system. And so now you only have to do, it turns out, a 1D Fourier transform on this data. And then you'll end up with a DC spike, and you end up with your contributions around that DC point, plus and minus. But they are representative of the spectral phase of your unknown pulse. So you isolate one of these side lobes that you see, and you can extract out the system. What's really neat is he actually said, okay, now what if in one of my arms of my interferometer, here's my microscope objective, and what if I use a near field tip and I measure these spectrograms as a function of position. He can actually completely map out the electric field, and really just then he can propagate it and give you a complete movie of how your light is focusing in space and time through the system. So this is called C-tadpole, and what I like about it, it doesn't seem not quite clear here, but it's very intuitive. When you see these interferograms on your spectrometer, you develop, it's really easy to see what's happening. Oh, I've got third order, I've got second order, et cetera on these things. And then you can get this complete space-time picture of how the light is focusing. So it's really powerful. And these are classic examples of what Rick has done with this system. So there's what it looks like in the spectrometer. The math is pretty simple. You Fourier transform along this axis. And then, yeah, you can really watch it. So this one's neat. So you can see that the colors are not aligning. That's why you've got this chromatic blur coming out. And then you really get this complex focus right here where you've got this radially varying delay. So not all the light arrives simultaneously right at the focus. So you get your integrated pulse duration is longer than what you think it is. So,
is this commercial?
Yeah, so the good news is I've been kind of bugging Rick about this for a long time, and so he is going to start trying to commercialize this for microscopes.
Okay.
Yeah.
And tough question, what's the acronym for C-tadpole?
Temporally analyzed dispersed pair of optical light, something like that. Yeah.
Amphibians.
What's that?
There's an obsession with amphibians.
Yeah, he does. It started with a frog, frequency resolved optical
Was
gating.
it no-nonsense Grenouille?
And Grenouille, I can't even begin to remember what that one is.
Nonsense.
Oh, is it? Oh, is it? No. I remember one year I worked on something with Rick, and then I called it Cobra for collinear background free frequency resolved optical gate. That was the original name of the one that I showed you before, but there was no having a non-amphibian. So that quickly got quenched. So Cobra acronym completely died. Yeah.
Must make it really hard to find acronyms.
Yeah, that's right.
This is the boa compressor, right? So he made an exception.
Yeah, I know. That's right. All those years later. So I actually felt like it was my little snake thing that planted that seed that finally manifested itself, So I got to give him a hard time about that. But yeah, and again, so I kind of apologize. This is just conceptually to plant those seeds of what these techniques can do, and then I'm happy to kind of map things out.
You can find boas in a swamp, but you can't find cobras in a swamp. It's swamp optics.
Yeah, it is. It actually, and it's being renamed. It's actually no longer swamp optics. It's like meadow optics or something. No, it's not that either. I'll have to go look. Yeah. Okay, but so here's we have actually used. Again, I like C-tadpole a lot because I can actually look at this and the images from the spectrometer, which is, sorry, I made that one a little bit too small again, and really see it, what's happening in real time. So for us, if you're interested in doing kind of pulse shaping, this was our pulse shaper where we actually used a Grisons, and then we've got the liquid crystal modulator. And then we just, because it's a linear technique, we could pick off the light before it went into the microscope, and we could actually measure the phase that we're imprinting onto the pulses in real time really easily. And but what's cool is if you're using a Grisons system, and I wanted to show you this because this kind of brings back the point. So we added 10 centimeters of glass which gives you about 5,000 femtosecond squared of dispersion, which might be about what levels that many of your microscopes are working at. And what we're able to show is that with this system, with the C-tadpole, you can actually, so there's what we calculated the phase to be, that dashed line, and there's what C-tadpole measured. So it's just really superb agreement. And then what we were able to do with the Grism here, before we even turn on the modulator, we were able to move it 500 microns from focus and just fractionally tilt it. And we were able to exactly match the magnitude of the dispersion of all the glass. So there's the dispersion of the glass. There's the dispersion now of our Grism as measured by the C-tadpole, and they're completely equal and opposite. So this made it possible for us to start with a pulse shaper that was fully corrected. Your pulses coming out and your pulses going to your focus are already quartic phase limited. And now you can use the full bandwidth, the full dynamic range of your pulse shaper to do any shaping that you want. You don't have to try to write the phase of all the dispersion in your microscope to your system. You're completely compensated right from the beginning with this system. Okay. So so this is kind of, again, so what, the disadvantages, oh, I didn't even put, there's no disadvantages to this one. Okay, but this is where kind of the new stuff hits, where I've kind of kept things in mind about what could we do really to still help facilitate the dual challenge of providing dispersion compensation for the microscope, but enabling you to do a pulse characterization at the focal plane of your microscope simultaneously. And we finally come up with a cool system, and this was actually the original idea by one of my colleagues, Dan Adams. And so the idea is pretty simple, is we set up a grating and we image it back onto a second grating. And in this case, it's just a 4F system. And if you do this, a simple 4F system is non-dispersive. So we go in with our sharp pulse. The grating takes the Fourier transform. So we end up with a Fourier plane here. So this is basically a spectrometer.
When you say non-dispersive, it's in the sense of imaging conditions.
Yeah, exactly.
But the pulse that goes through can still be dispersed by the pair of lens, right?
Yeah, there's a little bit of residual dispersion you can pick up here. Yeah.
In terms of temporal dispersion.
Yeah.
Okay.
So it's, but essentially, if I start out with a pulse here, it's going to come out basically the same coming out over here. So, but I've created this Fourier plane over here, and what is nice, it turns out, I'll show you in a minute, we can actually use, so what you do is you use this grating, you alter its position to compensate for the group delay dispersion in your microscope or your laser. So you can alter that position. So that gives you second order dispersion compensation. So this is your dispersion compensation system. So, but what you can do is if you actually, as we show here, if we go into a doubling crystal and we spectrally resolve that light, and this could be, I'll show you how we embed it into the microscope as we go along. If you take and spectrally resolve this light and you put a slit temporarily inside your system, what we do is we record that second harmonic light as a function of this slit position. And it turns out that is a kind of an equivalent of a frog trace by doing this. So now I've gotten rid of my interferometer. I don't have anything complicated. I don't have any timing to do in the system. And I simultaneously have a system that can compensate for my dispersion. So I can take my oscillator, I put it through my dispersion compensation system, which for a lot of you is some prism system. I put this in instead. Now I'm in line with my microscope, and whenever I want, I can actually just put a slit inside this system and scan it, and I can actually measure this trace at the focal plane of my microscope and measure the amplitude and my phase of my pulse there at the focal plane of the microscope. So for the first time, it's kind of doing two functions. You're almost getting it for free. And so we're these days we do lots of work with fiber lasers. So this is the actual, this is what a kind of a spark trace looks like. And this is taken at the focal plane of our microscope, and we're using a home-built ytterbium fiber laser. Ytterbium fiber lasers have this kind of Batman spectrum. So we retrieve the spectrum. There's the phase, and there's the amplitude of our pulse at focus. And it's kind of Batman. It's kind of square-like, so you always expect this kind of sync squared type behavior. It's retrieving it beautifully. The other thing that's really nice about this system is that, how do you know you made a good measurement? When you retrieve, so you can check that multiple ways. One, you retrieve the spectrum. So you can actually say, oh, does that look like my measured spectrum? So that's one metric to tell you how good of a measurement you made. The other thing that you get for free is you actually get the image of the slit out of your retrieval. And so literally what we do at that point is we take a pair of calipers and we measure what is the width of our slit that we use for the experiment. And then we measure the retrieved image and see how well they agree. So now we've got multiple metrics that say, oh gosh, I've made a good measurement, or my measurement is terrible and it doesn't work. And I need to do it again. There's something wrong. And now here's just an example of the traces where we've just kind of put all kinds of pulse shapes through it. So you can really see how these traces change. And then as I go along, I'll actually show you a little bit more about how we can embed this into the system. And again, for me, like frog's the gold standard, so I always like to compare everything to frog. And what these tell you is that we literally can retrieve a pulse from frog, retrieve a pulse from spark, and they just lay right on top of one another. Yeah.
Just a question, so is spatial chirp information in there, or is it a problem?
Yeah, so it's a great question, because I think it gets down to this down right here. So as soon as we move that grading off of zero dispersion, we end up with a beam that is spatially chirped. And so for me, I wanted a technique that would allow me to measure the pulse width even in a spatially chirped beam. So that's the strength of this, but it actually won't tell you the magnitude of your spatial chirp. Okay, so but we've got other ways, simple ways to do that. I'll show you as well. So what's neat is that even though I've got a spatially chirped beam over here, and it's not huge, this pulse measurement technique still works. And we'll show you. Okay, so, and what I guess the take-home message is that I think these start to become really accessible tools. You need to compensate. You've got an inline system that you can use to compensate, and now you don't have to set up any interferometer. You can just if you can take two razor blades and build a slit, you can do this method. So you really get the amplitude and phase of your pulse out of the system. And so here I've kind of summarized. This is what it looks like. Oh, so there's an actual Zmax ray tracing of the system. And I got the advantages is that especially in terms of transmission, is these gratings these days, you're going to get greater than 90% throughput through the system. So your pulse compensation system is barely going to attenuate your beam. So that's great. And now you can measure your pulse. Disadvantages, we're only correcting for the group delay dispersions, second order dispersion. And like I said earlier, now my third order is going to add to my glass in the system already. So we need to track that to make sure that there's no bad effect for that. So, and then you can imagine that where we're going a little bit down the road is that we're going to replace these with Grisons. That's really going to be absolutely ideal to do all of these things. And then, so it looks like we're getting close to probably needing to take a break, but I want to try to get through this if I can. Yeah, so we'll break up. That way, when we come back, we can just jump right into the imaging. But this was really totally inspired by talking to Spencer on these big systems, where what we did is we evaluated that if you're using 50, 60,000 femtosecond squared of dispersion, and you're using it at these different wavelengths, how big is my spatial chirp and how much residual third order do I actually have? So is it really practical? And so this is, so for 50,000 femtoseconds squared, it turns out I end up with some residual third order, so I've got that ringing on there. And I can actually account for how that ringing is going to mean that my efficiency based compared to a transform limited pulse is going to be down to 76%. Okay, that's my pulse shape factor here. But my efficiency through that compressor is really high, 92%. So if I take the product of those two, my net gain in signal is like 65%. Is there a spatial chirp? Yeah, it's really mild, and I can explain what this is. This is really a quantitative metric that allows us to tell you how badly your chirp is. And then I compare it to, like, here's prisms down here, where this is for 60,000 femtoseconds squared at 910 for SF57 glass. You end up with a little residual third order there, so you don't get perfect. So you take a little bit of a hit there. But here I think I was pretty generous that the throughput of a prism compressor is 75%. I don't think I've ever gotten one to work that high, but I tried to be optimistic. So you take a hit there, 50. So you're actually, there's no beam aspect ratio, but it's your gain is actually smaller than we are up here. So it really compares favorably. Yeah, if I wanted to, and this is for, yeah, anyway, this is kind of a, really shows that even for these really large systems, this is huge amounts of dispersion. So it compares favorably. Oh, but now I've just got a couple more, one more slide, and then we'll stop, because this is one of my favorite things that we've done. So this is the kind of the measure, the modeled trace with the residual third order that we should see through our system, where we've got the fiber laser and everything, and it's just ever so slightly, it's got, this wing is slightly higher than that one. That's the result of the residual third order in ours. But this one I'm really proud of is, I think this is one of the very few measurements that actually shows uncertainty in the pulse measurement at the focal plane of the microscope. And so you can see, not surprising, where there's lots of energy in the trace, our error bars are so small you can't really even pick them out. And then the uncertainty in the measurement's really in these wings, where there's less energy, and it's kind of gratifying. When it hits these 0 points, that's where the uncertainty kind of spikes up, which is not surprisingly, but I like this one. And again, now we've done everything with second harmonic. Now we know how to modify our retrieval algorithm. So this is going to work with a cover slip as well. And so then you'll be able to do these spark traces with a cover slip in your system as well. So then it's going to be very, far-ranging in terms of the, I mean, just the tunability of the lasers, etc. So with that, I'm going to stop maybe right there, because I think we're already at our first break. And hopefully you're still listening. There's my ear. But we'll take a quick break. And then for the rest, the second part, we're just going to talk about, and I'm going to kind of go back in time again. And it's almost the silver anniversary of this paper. But this is to this and kind of some other stuff that we've done to motivate things. So if you want to make a real, so I was really fortunate as a graduate student. I got to work with Fred Brackenhoff. He was one of the pioneers in confocal microscopy. And kind of what he instilled in me, and hopefully you see it in my design, is really making simple, robust optical systems that work. And so this is believe it or not, this was the first video rate 2-photon system. And so it uses an extended source. You use a cylindrical lens and create a line. It goes through a dichroic. It hits this mirror, and and then that mirror scans it across the object. It's an extended source, so now you take the fluorescence, comes back here, off the mirror, gets descanned, hits the dichroic, goes through a slit, so it mitigates scattering except along the length of the slit, and now hits the back of this mirror and gets rescanned onto a camera. So this little head is very small. It's, I don't know, about 8 by 8 inches or something like that, and you've got a video rate system up and running. So the challenge, though, is that it's a simple design, very elegant, straightforward to reproduce. If you wanted to build a second video rate system, this is something to consider. The weakness was the scattering along the slit. So we were kind of inspired by this, and we said, okay, well, is there a multifocal approach that we could use? So going to extended sources to kind of help mitigate that. And that's where we started developing all these multi-beam systems where we've time delayed all the beams with respect to one another over durations that are longer than the fluorescent lifetimes. And we do photon counting everywhere. And so this was one of our first systems. So gosh, yeah, I hate to say it. Yeah, it started in 2007 already. But this was a system that had 6 beams, all time delayed, all photon counting. So this is actual photon counts on these axes. So we could do simultaneous 2 photon, third harmonic, second harmonic generation imaging with 6 beams. This is a trigeminal nerve from a fixed adult mouse in SHG and THG. So we get 18 images. We can kind of get video rates with this.
Is that autofluorescence?
What's that?
Is that autofluorescence you're looking at?
So this is second harmonic generation here, and third harmonic generation here. And then we've got I don't show the fluorescence
That's
channel.
label free.
Oh, yeah, no, for the fluorescence, yeah, for most of the fluorescence we didn't do it. These are label free,
Yeah.
but the fluorescence was usually with a label.
Okay.
So this is kind of neat, and we got quite a ways with all this stuff.
There's a question.
Oh, yeah.
How many beams are there?
So there's actually 6 beams. This is actually one laser. And I still...
But how many beams do you split from one laser?
Oh, they're all time delayed out of the output coupler of the laser. So I can show you how we did this if you're interested as well. So I built so what I did is I built an extended cavity laser which has a low rep rate. And then to make it compact, I folded it. And then what I decided is, oh, wait a second, if I make the fold mirror the output coupler, all the beams are automatically time delayed. So that's what we did. So you get all 6 beams coming out of the output coupler of the laser, and they're all automatically time delayed.
How many beams can you scale up?
I never went past 6. How many do you want? Yeah, yeah. So that was and then we had a lot of fun with this because now we could just with this extended beams, you could just do all kinds of things. So we could do multiple depths. So here we just focused. I'm just showing a couple of the beams. Yeah, we add deep focus to one arm relative to another. And now you can do simultaneous multi-depth imaging. You can actually, then you can just, think of every possible iteration. So here we did simultaneous second harmonic, third harmonic at multiple polarizations simultaneously. And you get just amazing contrast by just having the polarization of these harmonics in the different arms. Believe it or not, you can actually already do, by playing around with the beam shape in one arm relative to the other, you can already start to do enhanced resolution. So here's the normal resolution of the microscope, and then by playing with the beam shape, we could get, or you can already resolve things much better in this system. And if you look at the lineouts, this is what gave us about a factor of 2 enhanced resolution. It was fun to put photonic crystal fibers in one of these arms, and now this is doing multiple wavelengths all simultaneously. So we got excitation, so we got detected, yeah, so we're at 900 nanometers, 1040, 1200, and 740 nanometers kind of simultaneously. And then this did work at video rates. So here's 6 frames simultaneously at 30 frames per second, and we imaged inside of microfluidic channels, which was also part of what we did. And then one of the other fun things that, and we talked a little bit about this week, is that once you're doing the photon counting, you can actually get rid of the filters in front of your PMTs. You don't have to have all those different channels. Just get rid of your filters, and then just use the time resolution to see things. So here we took fluorescent beads, and this is cornstarch, so it's kind of an ugly image, but no filters in front of the PMT except a blocking filter for the fundamental. So you're getting both the second harmonic and the fluorescence in the same PMT, and because we're doing photon counting, we can see them both simultaneously. So if you have a lot of losses due to filters, this is kind of a simple way to really kind of increase your throughput. Okay, so that was nice. These are pretty complex systems. And so was there a compromise that we could do? Could we go back to our extended line source and its simplicity, which is really like 100 beams in parallel, because it kind of gets back to Shea Wong's question, could I do 100 beams? So that's actually, when I presented that initially, that system, Winfried Denk asked me that actual question. ages ago. It says, well, I've got schemes to do 100 beams. How I do 100 beams simultaneously is our next topic, as we really go back to our line. And what we're going to do is now we've got a continuous source. And so each pixel that we'd like to resolve along that is our beam. So now, in principle, it does look like 100 beams or 300 beams. But I want to get rid of the camera. I want to go back to point detection. So if my system is scattering, I don't care as the light comes out. I can reassign the spatial position, whether it's the imaging with the fundamental, second harmonic, third harmonic, or fluorescence. I want to be able to reassign it. So what we do is we take these masks and we put them in a stream, in a path right where we create our light sheet, and we spin it here. And what happens is we actually modulate in amplitude each pixel that we'd like to resolve at a different frequency. And so this first pixel is blinking on and off at 30 kilohertz, and the next one's blinking off at 35 kilohertz, and then 40 kilohertz. So it's actually linearly chirped in terms of the frequency rate, and that's what dictates this design. And now I can go in with here, I can hit an object, and I can collect the light, and it can be nonlinear emissions or whatever. I can just collect it all on a point detector, a photodiode, photomultiplier tube. And literally all I have to do is I get a voltage versus time signal, and I can Fourier transform that, and I'm going to be able to get the spatial position out. So this is a more beautiful 3D rendering by Jeff Field at CSU and what this guy really looks like. There's our spiffy mass spinning. Here's our system. And then just to show you that if I picked 3 pixels along that line, they are blinking on and off at different rates. And my voltage versus time signal that I get out of my detector looks something like this. But if I Fourier transform that, I can get back and I'm not imaging anything, I can get back the beam profile. So now we've got extended source imaging with point detection. So this is where now I've got massively parallel beams in a sense. And so to understand how we get extended resolution out of this, you got to switch from the time picture and prep yourself for the spatial frequency picture as well. So that's what this does. So if I'm looking down on the mask, think of that mask as actually acting as like a diffraction grating whose ruling lines per millimeter is changing as a function of time as you rotate it. And if you look, and I'm ignoring higher orders here, just for simplicity today, we get a 0 order beam that comes through, a 0 order light sheets, and then we get the plus and minus orders, and I'm just showing the plus or minus 1 orders that come out. And if you think about it, when I take a line and I hit a mask, I've got this modulated beam. Oh, that is just the interference of beams coming in at different angles to produce these lines. And so from the top view, I actually can see as I spin the mask, I really can see these light sheets, and they breathe in and out as the mask is being rotated. And they produce different spatial frequencies as a function of time on my sample here. And I can use anything I want to detect. I can image with the beam itself. I can do linear fluorescence. I can do 2-photon fluorescence, second harmonic, third harmonic, you name it. It works with all of them. And this is the side view. If you're looking down through the side, what the system looks like. And so this is just now a movie to show you that there's my mask, and this is the entrance pupil to my optic right here. So you'll start to see the light sheets, what they look like projected on the back of the pupil. And now this is the intensity at that image plane. And then if you were to do a nonlinear process that scales like over I squared or whatever, this is what it would look like. Okay, this is your choice of nonlinear process. And this model is pretty complete. It really includes vignetting and everything with it. So let's see. There it goes. So you can really see at the back the light sheets and how they producing this spatial frequencies that are varying as a function of time. So that's why it's called spatial frequency projection modulation imaging. I mean, it's kind of the worst acronym ever because it doesn't, it's spiffy, but it doesn't add up correctly according to our rules of acronyms like Frog does, but yeah.
Is that the real-time spin of that disk?
No. Oh, that is just showing, yeah. So we can go a lot faster.
I mean, what kind of rotation rate you use?
Full range. So right now we can spin this, in this system, we'll spin it up to around 400 hertz. Yeah. And then we'll show you how to go much faster towards the end of the talk.
It's an absorption mask, right?
No, it's amplitude. So it's just, it transmits at the white and it
That's
just
what I
reflects the light, scatters the light on the black part.
Got it.
Yeah.
So this shows the scan basically the x-axis, right?
Yeah, so we're going to focus, we're going to have high NA along the y direction, and we're going to have an extended field of view along the x-axis. Yeah.
So there's no scanning in the y-axis?
Yeah, no, you do. It's oversimplified. So you either scan the specimen or you add a system in there to scan that beam. Yeah.
So in terms of like preserving photons, is there something that fundamentally prevents you from using a phase mask to generate that pattern?
No, there's not, and you
Okay.
can, and there's real advantages to doing that as well. Yeah.
Yeah.
So yeah, no, yeah.
Is that an optical illusion? Or it seems that the disk at some point is changing.
Yeah, it's the moire of our projector. Yeah.
So it's constant.
Yeah, isn't that awesome? And what's weird about the moire, and you'll see it happen throughout the talk, is often it reproduces the spiffy mask. And yeah, oh gosh, yeah. Okay, so yeah, let's see. So which one? Oh, okay, yeah. So here I want to show. This is a little bit a different simulation. So we actually make the mask in reflection in rectangular coordinates or in polar coordinates in transmission, so we can spin. So we can either spin the mask or move the beam. And this one is to show you a little bit more about how what we would do is that if we projected a square beam on our mask, and it allows you to think in both the time domain and the spatial frequency domain. So we're going to spin the mask, and you're going to see there's 6 points light up here. So you're going to see how each point blinks on and off at a different rate. But you'll see the spatial frequencies as a function of time in here. And this is the signal that we're going to detect, what it looks like as we detect it. And then when we're gone one revolution in the system, we're going to take the Fourier transform, and you should see a rect function, because we're just assuming a square intensity profile. So again, just to kind of build up your intuition. So each of the pixels blinking on and off at different rates, they all sum up to produce this spatial frequency projection. And we're going back. There's our time signal. And we're almost all the way through. And there it is. And then take the Fourier transform, and there's our reproduced system. So we're getting our one-dimensional images out of point detection. And so we really don't have to worry too much then if our light's scattering, we've got an extended source, so it kind of overcomes one of the limitations of our original system.
Sorry, the intuition is a little bit failing me because maybe I don't understand some points. What happens if you have a lot of fluorescence in different points of your field of view? So this is a sum of many of these little squares, or you always go point by point, and that's so you don't have this problem.
So we're projecting that line all simultaneously, and we're going to collect the fluorescence from that line, from that one line, and not, yeah.
I see. So basically, this give you the profile of that line.
Of your object.
Fluorescence profile of that line.
Yeah, of your
and
object.
Then you move it around. And
Yeah,
you reconstruct.
yeah, that's right. That's right. Yes. Yeah, so we're going to, yeah. So just like you would raster a point, but now we're rastering a line.
So you really need the disk to finish one round of
Yeah,
operation to
yeah,
flash up image.
Yeah.
So can you use just quarter of the
Yeah, absolutely. Yeah, absolutely. So, yeah, this is way overdoing it, because look at how many times I'm sampling that. So if you think about it, by Nyquist, I don't need to sample that frequency that many times. So that's how you kick up the rate. You just say, okay, now what if I put 6 or 10 zones in there? Yeah, yeah, that's a great question. Yeah. Okay, so this is what it looks like when you ray trace it in something like Zemax. And spin it, and then when you take here I just used a Gaussian source, and I Fourier transform it, and I get the image of the source. Okay. But now there was a surprise waiting for us when we were actually taking the Fourier transform of these signals in the lab. We noticed that when we looked at higher carrier frequency, there were other images there for free. And it turns out those other images are all at much higher resolution than the fundamental image. So we were able to get enhanced resolution out of the system for free. And it was really Not what we intended, but it's actually what happened. So, okay, there we go. So, and this is the how it works, is that normally your cutoff frequency in these coherent cases is really defined by the NA of your lens, and that's this half angle between the marginal ray and the chief ray. There's our cutoff frequency, and there I've actually measured, that's the actual measured spatial frequency between a light sheet going here and here. But if you think about it, what if we could actually separate the image that would be created by light sheets going down at the marginal ray angle? That cutoff frequency is much sharper because it's at double the angle. So what I did is I've actually allowed light now to go through the edges. And you can literally just put a wrench here and block down that central light sheet. And you can see you get twice the spatial frequency. Yeah.
So what's the diffraction efficiency of your spiffy mask that you're using right now?
It's perfect. Yeah. So it's, of the mask that we're making right now, so we get, most of the light goes into the 0th order beam, and then we've tried to produce a 50% duty cycle on the masks, and that gets rid of all the even orders actually, so we ended up only with the odd orders. And so we've got light inside the plus and minus 1 orders and some of the higher orders as well. And so I actually haven't measured it, but it's pretty good, but there's too much in the 0th order, to be honest. Yeah, that's what dominates, and that gives us noise. Yeah, and we got to optimize that, and that was actually kind of what we want to do with the phase mask, actually. But yeah, and we can, so, all right, so that's the name of the game, is actually, hopefully you agree that, if I could just see an image formed by the light sheets that just travel through the edge of the beam, I'm always projecting higher spatial frequency content. And so here I'm showing as little math as I can, but this is the actual expression then for the intensity profile at the image plane. And it looks like, look, there is a term with higher spatial frequencies. And the spatial frequencies, of course, you're doing spatial frequency projection modulation and image as a function of time. That's why it changes as a function of time. And and then I can break these out. So it really is that second order term down here is the interference. So I got of only the plus and minus 1 terms. So I've actually got my higher order images embedded inside my signal here. Okay, so it's there if I can get to it. So what we do is then your detector is, we spatially integrate over all of this signal, and you've labeled it with a fluorophore or something. And so again, so this is what the measured signal from your detector looks like. And ultimately, you can take that intensity profile to any power. We just say, okay, and then we're hitting some fluorophores or whatever. This is our fluorophore distribution. That's what beta looks like. There's our voltage versus time signal. But now if I take the Fourier transform, I can get my signals out. But what's nice is it turns out that those marginal rays, when we take that Fourier transform, that image formed by those marginal rays is at twice the carrier frequency. So you literally get it for free. It's sitting out there, and this is what we noticed. Like, we were in the lab, we're taking images. We were expecting this guy, and we kept seeing this guy floating out there. So what the heck was that? And that's where we had to go back and look at what was the picture. We were really set out to do extended source imaging with point detection. And then we realized that what was happening when we started taking a look at this diffracted picture about the influence of those marginal rays. So you get it automatically.
Fundamentally, is this equivalent to doing structure illumination in the temporal domain?
Yeah, basically it is. We're sweeping our space, but we don't have to take 3 sets of data and do that. It's there. We're sweeping continuously. Yeah, that's right. Yeah, that's right. And we got a nice point detection. So yeah, so we really get these two, and actually you can just see this is just shows you that, if I look, there's the interference with that marginal ray and the central ray, and it's always lower spatial frequency content. With these two guys, it's always much higher. And if you look, the rate that this 0th order is separating from the center is much lower than, these two are walking off from one another at that same rate. So they're at twice the frequency. So it automatically encodes this image. I mean, this never happens, right? You get it for free at a carrier frequency that's easily separated and detected. Yeah.
So what you're saying is that you get a factor 2 in resolution, basically.
Yeah.
Are you referring to factor 2 in resolution with respect to what you would get with coherent imaging or incoherent imaging?
With coherent imaging.
With coherent.
Yeah.
So you
Yeah.
basically are equivalent to the resolution limit of incoherent imaging systems.
So, well, let's see. I got the modulation transfer function coming up. So I'm not quite sure. Yeah. Which?
Yeah, you mean coherent imaging with half the wavelength, or you mean?
No, as in like if you're looking at like a transmission image through a microscope objective with like laser light versus incoherent light, you get a factor 2 in resolution.
When you use the coherent light.
You lose a factor 2 in resolution when you use coherent light. Right?
Yeah. So we'll show you. We got all those aligned. Yeah. Here in just a minute. Yeah. Yeah, to make sure. Yeah, and we'll put it in. Oh, and then okay. So, yeah. So this is kind of the general term right here. And gosh, this one's kind of complicated, but and this one shows our original. It gets kind of back to your point. So now once we start going to higher intensities, this is our more general signal that we're going to detect, and this is where we can start pushing past kind of the traditional resolution limits of all of these modalities. So for example, now we're just going to add a single bead, and I really got to take this expression and I'm going to raise that to the whatever power of the nonlinearity it is. So the enhancement that you start to see, it goes, so now I'm going to start to see 4 terms, like if I do a second order system here. And so now I can actually see, like this here, we're just doing looking at in this case, I think it was a 100 nanometer fluorescent nanodiamond. And we're going to be able to measure the point spread function. And here is the MTF of the system. Yeah, we've done it multiple times with multiple different modalities. And so this is your net signal. We can take the Fourier transform of it, and you see all these different images at all the different orders here. And we can actually isolate each one and go back into the time domain. But we're actually able to watch then and measure based on this, the individual cutoff frequencies for the system and actually the point spread function. And this is our very first data. And so what's interesting, there is quite a bit of structure here, and it was our initial mass and stuff. And we've really improved on all of this initially. So, I wanted to show, okay, actually, so I've got a movie that goes there. Oh, there it goes. Yeah, so now you can actually see there's our signal, and this is where we're really working on this guy and isolating each one of these. So you can see the individual terms and how it builds up, and each term leads you to a little bit, an ability to push that cutoff frequency further and further out. It turns out here there's a lot of noise initially because in our first mass, we have a lot of interference from other orders and stuff that are adding structure. So it's not as clear in these first initial images, and that's where we put a lot of work into it. And so, yeah, so here's our first order image from 2 photon that we would get, and here's the second order image, and hopefully you can see that. Just looking at that, you can see it's a sharper resolve. They'll look a lot better up here on my computer. And this is actually going into rat tendon and looking at all all orders of this images, all 4 orders of the image, and they look sharper, but again, down here at this point, we've got enough noise in our image that we're really not gaining that enhancement at this point. And that's where the mask design has come in, so we can really clean this up. So,
so this is experimental data with order 2 nonlinearity, right?
yes.
Do you have experimental data with like 3rd order nonlinearity and like effective frame resolution?
Yeah.
About 4?
No.
Okay.
And this is okay. So this is actually just showing you in linear modality. what it looks like in real time. So there's the spiffy signal. There's the Fourier transform of it, and we're just isolated this guy, and we're going to try to make this an open platform so that you can just grab it and use a FPGA. And what you'll see is that we're going to just drag a wrench through it. And you'll see that the wrench here is resolved. It's got twice as many pixels. You can really see it coming through quite easily. Yeah, so you can see that's really much wider than this guy. Yeah, as it goes through.
So can you I'm trying to match what you're seeing with the fluorescence image.
Yeah, so that was linear
All
imaging.
these two are it's one line again.
Yeah, we're always going with one line. And so maybe this will help explain it. So here we're actually measuring CAD telluride with 2-photon photoluminescence, 2-photon absorption. That's what the red is. It's all false color. And we're doing second harmonic generation imaging as well. And so we've got our line, and in this case, we're just going to drag our crystal up through it, and we can generate a two-dimensional image. So here's our first order image. So that's where we'd normally be. And now here, can you see it on this? And this, it looks great on my computer. So hopefully you can kind of see it. So you can come up a little bit after. But hopefully what you can see is that, on this guy right here, these layers are pretty blurred out. But you can really start to differentiate all these layers very clearly on what we would call our second order image. So this is where we're picking up a factor of 2.
Resolution along that axis is still the same, right?
Correct. Yeah. So this is only along one axis. So it's beautiful. We pull up ours. Yeah. And we'll get to that. Yeah. That's right. That's right. So okay. So this kind of gets so now. Yeah. So here's where we've actually kind of plotted the R OTFs for spiffy are in along these lines, and now we can really comparing it for 2-photon and 3-photon. And my hope is that you can it really seems to make a difference, and hopefully in understanding your images when you really do start to, so your cutoff frequencies are the same, but look, you really are gaining this more bandwidth towards those cutoff frequencies. So I think it could have a real impact there. Yeah. And then we go through it, we try to, so the way we've done this is we've measured with fluorescent particles that are way below the spot size. We've used fluorescent, so we've used fluorescent spheres, we've used fluorescent nanodiamonds. For second harmonic, we've used small barium titanate crystals to go through and do this. And then for just pure linear imaging, we can actually use just like linear or Air Force targets. And so this would be our first order image, and there's the second order image, which shows that we get the improved cutoff frequency. So, and then you get the doubling of the number of points that you're able to sample. So at this point, I think we've gone through about every iteration that I can possibly think of in terms of trying to characterize and really show the gains relative to these things. And we've calculated it and put it tabular form against all the different modalities that I can think of to show you how it compares as well. So this, yeah.
It seems that you should be able to fuse this information computationally and actually increase even more your resolution by combining what you see in order 1, 2, 3, and 4.
Yeah.
Is that the case?
Yeah, I think so. Right now we've kind of done the easy thing, right? Is that okay? We've got all these orders here, and we're isolating one and looking at it. But you're 100% right, in my opinion, that what you really want to do is a full retrieval based on all of these and assemble the image. And that's what Randy Bartels is working on right now. Is just saying, gosh, look, this is going to make our images much better. If you don't isolate, you really use everything. So that's exactly the direction we're headed, and that's Randy's.
This reminds me a little bit of a wavelet decomposition. I don't know if you guys draw any comparison.
I haven't personally, yeah.
But fundamentally, this reminds me a lot of that nonlinear structural illumination microscopy paper that was published, where you would illuminate with a sinusoidal pattern.
Yeah.
And then as you ramp up the nonlinear, you
Yeah.
basically start folding in higher orders.
Yeah,
That's
yeah, yeah.
exactly what you're doing in a temporal domain, so you don't have to
Yes.
find those like odd materials.
And we're doing it with point detection as well.
Yeah.
So we can go through scattering stuff. And that, I mean, you bring up another good point, because the other thing that we see, like when we apply it to linear fluorescence imaging, is we start to saturate things.
Yep.
And so we're going to be able to exploit exactly that method.
Mhm.
Yeah. So so this compares our OTF, and actually for 2 photon, 3 photon with all the orders, and I've got exactly what you want for coherent, incoherent imaging on another slide. So I can show. And then for those cases, I actually like to follow the Nature paper. Nature, I think it was in Nature, where they suggested using kind of the Zernike stars to clarify, and that's what we're using as well. So take a look and put all of this stuff in line so we
But
can.
in your spinning disk, do you
Yeah.
really need the low frequency information?
No.
So,
Yeah. You're right. Yeah. So this gets to the next point, is that really what we do is, again, we're shooting out the line, and then we either got to scan the line in the Y direction, or we got to move the specimen. And then we end up with kind of the frequency support of the NA in the Y direction, but then we get the extended resolution in the other direction. But now we're really taking the steps of just, if we rotate the sample, we can actually add all this extended support. So we haven't gotten very far on this yet. And I'll show you just a real, there's our just imaging spheres. There's that 6 angles, and hopefully this is once we add everything together. It's really giving us the nice frequency support in all directions. So.
What's the computational method to merge those data streams?
Yeah, so that is, it's slightly different than the traditional tomography. It's well, we call it Fourier computed tomography, but and again, maybe that's something we can go over here. It's just a little bit different, but it's got a couple of steps you have to interchange, because where we start out, but it's really just kind of drawn from the tomography folks. Now, the other thing that we've done, what we had the realization is that if you took at any given instant, you looked at, you froze the mask, and it really it became clear to me that, oh, wait a second, I've got an interferometer built into this system. So I've got a 0th order beam and a plus or minus 1 order system. And so what I want to do now is I'm going to actually detect back through the mask on my point detector. Okay, and I can just collect it in front. And so my hypothesis was here, because I've got a common path interferometer built into the system, I should be able to do phase imaging. So then I went on the search. I went to like Photonics West, and they have a whole section on phase imaging, and I sat down and what is a phase object? And it turns out it's different for everyone in the world. So this is my definition of a phase object. Okay, so I wanted to show it. So what I did is I just took a glass window. It's flat, and so I should just initially see the beam coming back. And then what I do is I take a CO2 laser and I pump that window from grazing incidence with just a burst of the CO2 laser energy. It's absorbed on that window, and we've got it calibrated so it only creates a dimple that rises up due to the heat about 1 or 2 microns. And then it relaxes and settles into things. So for me, that was a phase object. And I'm imaging this now with a working distance of about 60 millimeters. My line there is 20 millimeters long. So this is a long working distance system. But what we're able to show is we can get sub-wavelength axial resolution out of this system once we do this and exploit this interferometer. So what I've done is, before I fire the CO2 laser, I just see the laser line. It's basically a square intensity profile, super Gaussian. And I divide that out, so you don't see anything. Now I fire the laser, and now you can actually see the interference tracks. And so from this peak to this peak is about 1 micron. So we're really able to see sub-micron axial resolution out of the system over really long working distances. And the interferometer is built in. Nothing, no hard timing or anything to do with this system. And so this red part is really where I'm firing the button. And you can just see it, yeah, really just these waves moving in and out. And the students actually have a lot of fun with this, where they actually go into the glass and they'll machine channels into it. And they can hit it with a CO2 laser, and you can see the thermal expansion propagate up to these boundaries and reflect off the boundaries and die. So
You're also looking at the expansion of the air around the glass, right?
I guess, yeah, technically there's some, but it's just,
Or
yeah.
is it order of magnitude below?
I haven't, yeah, I really doubt it's much to do with the air, because it's so long-lived afterwards.
Oh, yeah.
The burst of the CO2 laser light is really kind of instantaneous. And so this, you really see it's really in the material.
Yeah.
And then, so then I had to kind of try to come up with other phase objects. So I had some clear lacquer in the lab that had been sitting on a shelf for about 10 years. So I took a drop of that clear lacquer and put it on a slide, and it's kind of separated from its different constituents of whatever lacquer is made up of. And I tried to image that. And this is the image I got of the lacquer as it dried. So it's very thin, nice field of view. And this is when we stick it right on our, it's not a totally fair comparison, but this is in our white light microscope at 100x. And it took 70 images to capture the same field of view that we're getting with a SPIFFy. But in just a pure white light microscope, there's just nothing there to generate image contrast. And with the SPIFFy, it just lights up. And what's interesting now is if I kind of zoom in on these, I actually can track out, I can see I've got the Z resolution built in, so I can actually see interference fringes there. And I think it's on, and this one's in the first order image. Here's our second order image of that, and you can actually track the fringing out to even a greater depth, and we use that as well as we're going out into a little bit higher. Okay, and there's my working distance and field of view. Okay, so now I'm going to kind of try to go through a bunch of topics. The art's getting a little bit darker, so we're getting closer to the end here. And so what can we do to extend it from 1D to 2D? Because as you've seen, it's really going along one dimension. How can we speed it up? And then also, this is an invention by Jeff Field, where we'll show you how to get things in Z as well. He's just starting to work on that. So it's actually really easy to do multiple cursors in this system. So in this case, we just created 2 line cursors, and we just put them at different zones within the mask. And then when we get to the focal plane, we can reposition those cursors however we want. And so now I pick up high resolution along this direction with one foci, and then I pick it up on the other direction over here. And this is just showing that, okay, there's the actual images of the beam, and that they really are separated out. So the images are separated out for free. And so here we are. We machine a kind of interesting structure in the glass. So this is with like this line cursor, and there's our second order image. And so you can see there's kind of the standard resolution, there's our enhanced resolution. And similarly, now this is looking along with the other cursor along the other direction. And our low resolution image, the standard, you can actually start to see beats here. But then when we go to the higher resolution image, it's really put together nicely. So again, you get all this kind of stuff for free on that. So that's one way to do 2D. The other way is to start to do multifoci, multifocal imaging with SPIFFy. And now this shows for the first time how we also integrate the spark system into our system. So here's our oscillator. And here's the spark system. That's going to do the pre-compensation. This is a fiber oscillator, so we already got to compensate for dispersion out of this guy. And so there's our spark system. It's in line with our microscope. So now we go to our SLM. And our SLM is what we're going to use to create multiple foci. Okay? So we're not going to use lines. We're going to use individual foci. And then that gets, so the Fourier transform of this guy gets image related to the SPIFFy mask. The SPIFFy mask, those images go to the focal plane. But now we can do multifocal, multiphoton excitation with single element detection. And it's really programmable as well. And what's nice is what you'll see in a minute with the spark system here is I actually measure the pulse duration right at the focal plane of this entire system as well. So what does that look like? So there's our spark system. And here's the series of spark traces as you dial this, let's see, in this case, this grating. As I move out that grating, I'm getting closer and closer to the transform limit. So this is the experimental spark traces. And this is where I end up with a transform limit. And I just pulled one of the non-transform limited ones out. So you could see that, oh, there's our Batman spectrum. And you can still see I've got a lot of second order dispersion in our system. And there's what my amplitude of my pulse looks like with that on there. It's not short yet. And then one of the things you always want to do to make sure that you're making a good measurement is here's the measured spark trace and here's the retrieved. And if those are not looking identical, you didn't make a good measurement. So you really, that's one of the metrics you have to make sure things are going well. Yeah.
How do you measure the spark traces?
So this is actually at the focal plane of the microscope.
So you replace it with a camera or something? What do you put at the focal plane?
Oh, so no, at the focal plane we can do all kinds of things. So we put something in here. So we've got a really thin doubling crystal that we put right there.
Okay.
And now we just literally, it was really easy. Right here we've got our Thor Labs spectrometer with a fiber from Ocean Optics. And you just put that right there to grab it.
Okay.
So the measurement is done right here.
Okay.
Yeah. Okay.
While you are spinning the disc.
No, that's you actually no, because you're not.
Where is the slit though?
So that's where the slit here. It's designed to be popped in and out.
And it's not shown there, but you put the slit in.
Yeah, you put the slit in. Your spiffy mask's aligned, so you're allowing all the light through. And then you scan it and make a measurement. Yeah. And what we'll say is we can actually turn on the modulator, create multiple foci, and we can actually do all the individual foci across the field of view. So yeah, a lot going on in all of this stuff. Okay, so so now I want to just take a look at this, where our spiffy mask is. And here's our traditional system. Cylindrical lens creates the light sheet. There's our spiffy mask, and that gets imaged all the way back here. But we really had the realization that, wait a second, this focal plane, that zone, conversely, and I'm killing the laser. It gets imaged all the way back to that yellow zone on your mask, backwards. So we really have the potential then to do complete two-dimensional imaging then with this system. So what we can do, and I'm only going to work with 3 spots here, is, for example, if I project these 3 spots, and as long as they're at unique radii, they are all modulated at different frequencies. But I can access anywhere I want to in that focal plane with this system. And so that's what we did. So here's an example of like 5 foci, and they're all modulated at different. This is only showing the sum of the 3 and the signals of the 3, but here's the actual retrieved foci in the focal plane, showing that we can kind of distinctly see all this. And this is nice, so that here's showing the multiple foci where we actually do the spark traces for the individual foci in the focal plane. And not surprisingly, because you're actually using the SLM as a diffraction gradient to create all of these, they actually give you lateral color as you move off axis, that the SLM does. And that lateral color distorts the beam spatially, and we can see it temporally. So here's the 0th order beam, and this was like the +1, and this is like the -1. And so the -1 is much worse. Now what happened serendipitously is we realized, so we're really using all the orders. Most people don't do this when they set up the SLMs like this. But remember, in our spark system, the beam has got a mild spatial chirp on it. The SLM is creating a spatial chirp. So we actually can rotate the spatial chirp of the spark system to negate the effects of the SLM. And that's what we do here. So we just show that, oh, initially I had a really bad spot, and I got a good one over here. If I rotate the spatial chirp, I can correct over here. So it was just purely serendipitous that you're picking up bad effects from the SLM that create a spatial chirp. We can actually correct for it at some level on average over our field of view by rotating the spatial chirp that from the spark system on top of it. So, and then this I'll go through really quickly, because now we just show that using a very, kind of my lab, well, we use just a lot of fibers to image, but just showing we can, with these foci, we can actually get separate images at different fields of view. So this is 2-photon fluorescence. This is doing second and third harmonic imaging. And this is all raw data. And it's kind of hard to see here, but you'll actually see that the amplitudes of the individual foci are not perfectly distributed. So, and we didn't correct for it at all in here. So you can actually pick out which foci is reproducing what. But this was simultaneous, multifocal, multiphoton SHG and THG in this system with the multiple foci. Okay, so this one, again, we don't go super fast. We rotate the mask about 400 hertz on this one. Yeah.
So, I mean, any super resolution.
There's no resolution enhancement in this one. Yeah.
Oh, okay, but okay, so I guess I'm sort of circling back a little bit to this question then. But you know, I'd expect them to require more photons in order to resolve, you know, finer details. Can you comment on the photon counts per pixel, or has that been quantified yet?
Yeah. So, it actually kind of leads in nicely to what we'll do next.
Okay.
But yeah, to be honest, right now we're just kind of saying that because we haven't done really a lot of dynamics yet. So the idea is that if you just kind of make simple arguments based on the fact that we're simultaneously got n sources, our pixel dwell time does increase, so we should see an increase in signal to noise due to that. But we also see a decrease in the signal to noise in like photomultipliers because you are detecting n simultaneously. Because that gets noisier from that perspective. But if you weigh those two against one another, we still think we win. And that's we got simple models that show that we should win regardless.
Yeah, I mean,
but we got to quantify it. That's kind of the next step.
Yeah, you've got great spectral separation. It seems like you can put.
Yeah.
You know, I mean, you already have like multiple traces in there. You can fill up the spectral space.
Yeah.
Pretty quick.
So I think at the end of the day, we should win. So this is one of the ways that we can go really fast now. This is kind of hot off the press. This was like done 2 weeks ago. Is where we machine a reflective mask, and now we scan the beam across the mask using a polygonal mirror. And so we can go very high speeds with this. And so this is using this rectangular mask where we go across it. And I just show that if you have your line this way and you scan it across, again, if you look at distinct points, each point's being modulated at a different frequency. And there's the polar equivalent. And so where we're at right now, we've actually got 8,000 line images per second with this particular polygonal mirror. And because this is literally hot off the press. I did this about 2 weeks ago. And we did something really simple is I actually just took this beam out, 100 millimeter focal length lens, and I wanted to image something really simple in transmission. So I actually imaged another spiffy mask that we had and put it on a photodiode, and you'll see. Yeah, so this is when my camera looks through this field of view, this is what the camera sees. So you can see the spiffy mask. And there's our spiffy image going at these rates. And you can see we've got a really kind of a larger field of view. And what I did is I cropped it. So this is, so now that's how far we got in a half a millisecond. So we're getting really good rates at this point. And then it turns out I'm using the polygonal mirror as slow as it can go, so we can go faster with it. But it really looks like for this system, we're projecting out, so we should be able to do 100 frames per second with this kind of a system. And then the other thing that we do that's interesting that maybe for folks is that we're actually starting to combine spiffy with micromachining, and it may be interesting in stuff for surgery. So here we've actually got a processing beam at 1 micron, and we're projecting an 800 nanometer spiffy beam, and we're actually cutting the material, and the spiffy's detecting the cuts, and we're blocking the beam on and off with the SPIFFE. So you can actually kind of see the surroundings. This is kind of lots of implications for us in terms of, it was developed for the kind of neurosciences, but it has lots of implications for advanced manufacturing as well.
And just to, not just manufacture, one of the things we were talking about last week was cutting the shell off of an egg.
Yeah, that's.
Can you do really precision surgery?
Yeah. So we're gonna really show that we can cut the shell off an egg and leave the protein, not denature the protein underneath it. So.
What is the application to brains?
Yeah. That's how it comes back around. Is to do a craniotomy. Yeah.
Interested in the Australian Aboriginal language, local the area where I grew up, the word for brain and egg is the same.
Oh, are you serious? What is it? Yeah.
Gabaga.
Oh, okay. Yeah. Maybe you have to spell that out for me because maybe we got a new name for a technique.
So you scanning from left to or right to left in this image?
No. So in this case, where we're processing, you're actually dragging the material through the system. So here we're cutting channels here. So we're actually making microfluidic plates here.
But
Now this builds on Emily's old work from ages ago.
but you're dragging in the horizontal direction, right?
Yeah, I'm dragging the plate this way. It can actually go in all directions. But,
And so you're doing like one line at a time, right? In the vertical direction.
yeah, there's my imaging profile. So I'm seeing that.
No, I see. That's what that is.
Yeah. And that is taking place much faster than the material processing. So I'm actually getting an image with higher resolution than the spatial resolution of my processing beam, and I'm getting many images before that material has moved. So.
And what gives you like the artifacts in the horizontal direction? Like for instance, there's like a green line and then
yeah, so here what we haven't done is, like in a lot of our images, we'll actually normalize out the profile. But this is like, again, this is kind of hot off the press. So we literally took a dirty piece of glass and you pick up different things in the glass.
Well, yeah, that's like that blue dot. Like
Yeah.
that's a piece of dirt or something.
Yeah.
But like, it seems like you're getting an artifact. Like, you have that like green line and orange line.
Yeah, you mean you're talking about this stuff?
No. Up in like the first quarter, like right there. You see like an orange line and a green line that
like
comes
this?
across.
Yeah. No, it's part of what you don't see is like we've actually processed we've got debris everywhere on this slide. So who knows? We got to really, like I said, we got to go through it with a really clean system. But we've made other channels everywhere. There's debris all over the place. So it's hard to say from that image.
Okay.
But we could just see it turning on and off as we kind of blocked it in the beam. But that's the direction we're headed. And now this last part is not my work, but I want to advertise it for, because there might be people here that are interested in it. And that is, this is called Coherent Holographic Image Reconstruction by Phase Transfer. And it's really Jeff Field and Randy invented this. And the idea is that what you do is you block one of your beams from the SPIFFE signal. So you've only got the 0th order and the plus or minus 1 order in it. And then they actually end up creating light sheets in the axial direction. And so now you've got 2 light sheets that are going deep into your sample, and the angle of the 2 are changing with respect to one another. And so their idea is that they can actually start to use this to start to do kind of light sheet imaging in 3D at depth, but you're all detecting it through the same objective. So a lot of the light sheet stuff you've got to look at orthogonally. Here, in principle, you could actually do it through the same objective. And I'll show you kind of what the method to the matter. I'm super impressed because I don't know how what their thought process was to discover this.
So this is escape with a phase mask or with a rotating disk modulating the wave, generating a light sheet through the same objective.
Yeah. So this is it's really going. Yeah. So it's producing this.
All right.
Yeah. And what they did is, and this is amazing. So what they have shown is that when they block one of the orders and they start only using 2 of the orders, that actually gives them a unique location of fluorescent particles in that XZ plane. So already along, and sorry, because I'll try to, if I can flash it up. So along the X direction, you've already got the unique location. But it turns out when they block one of the orders, your fluorescence is chirped. And the sign of the chirp of that modulation depends on which way you are relative to the paraxial focal plane, which is pretty stunning that they figured this out. So here's normal spiffy, and if I'm over here or over here, I can't tell you where we're at. But by blocking those orders, they're able to tell you which side they're on, which is really amazing. So, and then just to show how well it works is this, they took just some simple lens tissue and they've dyed it. And they've done 2 photon imaging here, but they've done it completely out of the focal plane of the system. Because they can measure the phase, they're able to measure the phase of these input beams based on the modulation of a fluorescence, so from this incoherent signal. And then they can do holography, basically, with it. And so here they are able to show that, oh, if I'm, I think this is, okay, it's right here. So this is like 40 microns before the focus, and this is 20 microns after focus. And so normally, and this is a 2D object, so just to show you the example. When you're out of focus, your image should be blurred by the defocus. But because they're able to measure that phase front where the specimen is, they can actually just propagate through it and they can correct for it automatically. So this is, you can see they get really the identical image in both cases. And so I think this is kind of on the horizon. And again, it was really Jeff Field's brainchild. And for me, I'm not really quite sure how he realized one day that he had this imprint.
Command voltages for AODs. If you want to focus deep or focus shallow, you send these chirp waves.
Yeah, maybe that's what inspired them, but this is kind of built in. So we'll watch how this evolves, because I think the potential is very interesting and how this could evolve into something as another tool in the way, because again, when you're doing spiffy, it's going to be easy to block one of these beams if you wanted to use this modality. And so, okay, with that, I'm all done. And so, yeah, thanks for your attention. I think I'm right on time. Yeah.
I have a clarifying question. So earlier you said you could either image your field of view by either moving your sample or by moving the beam, correct? Can you explain why you might want to do one versus the other?
I think almost exclusively in this community, you're probably never going to want to do specimen scanning,
right?
Because you really got to move quicker. So for a lot of what we do in my lab is materials processing, and it's just giant. You got a big part that you got to move through the system, and that would be an example of where we actually set it up to do both. So we've usually got a scan optic in there that allows us to scan certain areas, but then we can do specimen scanning to really put all these things together. So for a micro machine with femtosecond lasers, it's a great tool to be able to do both, but the specimen scanning. Yeah.
So if I understand correctly, you use the polygon mirror to sweeping your line
Across our mask.
Right. So
yeah.
I'm wondering, can you do like a 2D or a square illumination on your disk, and then have, so basically.
Oh, I mean, do all completely 2D field.
Yeah, complete 2D field, and then modulate the carrier frequency
of the pixels.
Of the pixels.
Yeah, you can do that, and the reason that we don't do it though is we found out, like, if you're interested in doing multi-photon imaging at all, it's just the power of the laser you need is too high. And so that's why we really actually feel that this geometry is more effective. Because now your light budget for supporting those two cursors is just more reasonable for most lasers instead of trying to do that whole 2D field. But we've actually made masks that can do the entire 2D field. And yeah, you can, but in general, just for most of our applications, the light budget's too high for the laser. So.
No, I was just thinking if you stack two spinning disks on top of each other and the other one have offsets from.
Yeah, that's exactly, yeah. So Randy's actually done that. Yeah, and they have a paper in optics letters where they did that. Yeah, just use, you got to be a little bit careful on how you relay it to the second one, but that does the full tube blown 2D stuff. And they did it for linear imaging. Yeah.
Excuse me.
Yeah.
Question about the chip system.
Yeah.
So basically you say it's like having a light sheet that bars basically.
Yeah, that's the way they've got it set up.
Did they try it on imaging, fluorescence imaging? Is there anything out there? Or
So they did that image I showed of the lens. It's not intricate, but that was done with two photon fluorescence imaging.
well, I mean, did they try it on a scattering mouse?
Not yet, not yet. That's where I say it's really just getting started. They've got it all worked out, but that's, yeah. So this is really kind of a preview, yeah. I mean, Jeff's got all the theory worked out, yeah. So, yeah, it's intriguing, I think, yeah. And like I said, I got lots of supplementary materials. So if you want to see how our optical transfer function compares to every imaging modality, we can do that. You can see where we pick what I call a factor of 2 and where it relates to any form of microscopy.
I might also miss this one. Do you have a mathematical description of this pattern?
Yeah.
And then, so you have a mathematical description of this pattern.
Yeah.
So what you showed us before, like that the composition was related to this.
Yeah, and where it derives from is basically I want to be able to use Fourier transforms. And so that's what determines the spiral kind of shape, is that way it creates a linear step in frequency between the pixels that I'd like to resolve. And that's where it's
Is it exactly Fourier transform or is it an approximation?
No, we just do regular Fourier transforms.
It's a real Fourier transform.
Yeah.
That's the correspond.
Yeah.
So the quality of
and we could do other things, yeah. Yeah.
The quality of your reconstruction is based on this mass being clean and rotating at constant speed, or am I missing something?
Oh yeah, no, you can, if your mask wobbles, we can correct for wobble. Yeah, if you have artifacts in your mask, yeah, that can kind of put some noise in the back there, but in general, we're doing pretty good.
So you're doing a direct sampling of the Fourier domain in one
yeah, but and things you got to be aware of, is well, wobble and stuff we've corrected for. We can correct for all of that stuff, but yeah, those are the things, and that's where I think that the longer term, where Randy's working on kind of inverting all this stuff is going to be much more powerful. But
so what you get is kind of a spectral ramp.
Yeah. You get
it's a spectrum, right? The approximation on a small window of your Fourier.
So yeah, I guess and again, you're projecting spatial frequencies and measuring that spatial frequency content as a function of time. Yeah, and then yeah, I don't know. Everybody's different, a little bit different language. Oh, and then yeah.
So you've got a lot of example things that you've imaged with SPIFFE. One of the things that should be nice about it, it should be relatively impervious to scattering. Do you have examples that you've taken like deep into scattering tissue?
I haven't, but that's where I'd like to go.
Yeah.
We need to do that.
I think that'd be really powerful. I mean, Nico mentioned that this is really similar in principle, the enhanced resolution similar in principle to pattern illumination, structural illumination.
Yeah.
It's one way and back.
What's that?
It's one way and back. Like you don't have to illuminate from the other side.
Yeah, exactly. It should work better in scattering tissue, right?
Mm-hmm.
There are relatively few techniques that work well in scattering tissue for super resolution.
Yeah. No, that's the hope.
Demonstrated that well. So a really powerful demonstration of that would be fantastic.
And I get my senior design students have a lot of fun with that. They're especially on the video rate system. What they've done to try to look at that themselves, but we haven't done it systematically and quantitatively. They literally take 2 layers of Thorlabs lens tissue.
Okay.
They put it on the incoming beam, and then they took 2 layers of Thorlabs lens tissue and put it on the collection side.
Okay.
And then with the camera, you can see nothing, of course. And then the spiffy's picking it out fine.
Oh, that's
And that's linear imaging. But I'd like to really build up systematic models that would be acceptable to this community to really measure that.
So this is a really, well, it would be an important result, but the objective and the PMT are on the other side. Is there anything preventing you from having a dichroic and shooting it to the side with the same objective, or am I missing something?
Oh yeah, no, because sorry, this is like, again, it's not, so we've actually do have a dichroic in here and are collecting it over here. Yeah, so it's just to keep this clean. Yeah, we collect in transmission and we collect in epi.
Because that's a very big difference with traditional structural illumination. That
Yeah.
you need to come in from one side of the other.
Yeah, no, so that's a fantastic point. Yeah, so again, yeah, we absolutely do. We detect in all directions. You don't need to do this. Yeah, yeah. Again, to kind of keep the schematics clean, just to kind of show people what we do. We detect everywhere.
The money is there.
What's that?
The money is there. This is like, I mean, with that modality, we can shoot that into a mouse brain and look at stuff.
Yeah.
Well, structural station,
and we're going to do that.
Yeah.
Yeah.
Yeah, that's why I'm excited. Yeah, I want to. Yeah, yeah. And the idea where we did the random access for, I need feedback from this community is that it's a little bit. So now with this guy, and I could actually get rid of this too. I could create multiple foci if you want, but that way you can go really deep as well with this system. Because now it's your light budget. And then if there's just certain features that you want to hit and like not heat up other things. So I think there's flexibility here. I don't know.
Now, what if when you have your reflection modality and you're trying to do diffraction, like interferometry measurements?
Yeah.
What do you see? Is it like is it localized at the foci? So that data that you got is based on the reflection imaging, right?
Yeah, so this is kind of detecting way back here.
Yep.
I'm not, so what?
Here your photodiode is on the other side of the sample.
Yeah, so this is in the epi direction.
I see.
Yeah.
So you're not using the data from the part on the right?
I did it not show. Yeah, so let me explain. Oh, shoot, I don't show it. So what I did is I imaged from this direction and this direction simultaneously.
Fair enough.
And this one doesn't show the fringes.
Got it.
Because you really are using this mask to put them right on top of one another and get that. You're changing the phase change that you see here into an amplitude modulation that only shows up when we detect it back here.
And let's say you have another phase modulation happening beyond the sample.
Yeah.
You won't be able to see it, right?
So you're saying I got, so now I'm reflecting back, so you have phase modulation in here or something?
Yeah, would you see it?
I would say probably, yeah.
Okay.
Yeah.
So it's aggregated phase fluctuation from the objective to the sample.
As long as it's, okay, so what I would say, if it happens outside of the 0th order beam, it'll manifest itself.
Got it.
Anywhere on that path. Yeah. 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 Yeah, and if you've looked at, I don't know, it's really powerful. And again, like these images are just a crazy far away. So 63 millimeter working distance, 20 millimeter field of view. Yeah. So
fast sampling is important.
Yeah, so that's where we're working. Yeah, so that's kind of my next. Oh yeah, so then that's where we're starting to do the video rate stuff, and so Spencer's promised to buy me all kinds of new electronics to capture this stuff really fast.
So on the slide you made some comment about the interference patterns. So are the ones on the right double in like spatial frequency?
I'm sorry, on.
Well, on this slide. You said
oh yeah, this is cool. Yeah, so okay, so we've got the interferometer. And the interferometer shows that before the fringe density, we can see them until the fringe density gets so deep, we can't pick them out anymore. But what's cool, this is the first order image, and here's the second order image. You can see it even on my computer. Now the pixel density is doubled, and I can follow the fringe into Z much better in that second order image.
The fringe spacing is still the same.
And the fringe spacing is the same between them, yeah. So, but it really allows me to measure that topology much deeper than what I thought. This one I love, yeah. Second, yeah. And if anyone has any interesting phase specimens, like I said, these are my idea of phase specimens.
That was a thing like a few years, many years ago, when imaging cultured neurons, for instance, apparently in there, you would be able to see, for instance, what the action potential happens.
Right, because of the index change.
Small variation of the pathway.
Yeah,
right?
yeah.
And you have the speed, so you'd be able to see propagation of.
I've seen that in where people have taken fixed slices and basically put it in an interferometer and they've imaged that. And here we have that opportunity to kind of do a similar thing if it was of interest where
It's not of interest to me. But
yeah, that's right. I know what you're talking about, yeah, because I've seen that, yeah.
Those people here might.
Yeah, someone else might, yeah.
It all depends on what the signal amplitude you get
Right.
out of this thing was, right? Because
Yeah.
if you could do single trial AP imaging with it, then great. But you've not, then it might be different.
Yeah.
And again, so for here, oh gosh, what's also maybe interesting is that, yeah, so this is where I'm using a laser to do, I'm imaging in the fundamentals. So now you've got it kicked back to, I want to say it's like a milliwatt that you're doing this stuff at. And you've got 10, you can have a 5-watt laser. So this is in the linear mode. You got plenty of room to grow. So yeah, so all great questions, and we're kind of mapping out all this space. But all right, so ready for lunch? Yeah, again. Yeah.